All right, now applications of optimization where we have constraints. Now, with applications, typically you have to find the constraint equation. So within the application somewhere, it should tell you we have a limiting value. And usually it's just a simple x plus y equal to some, again, constraint. So the first example, we have a farmer whose profit per square foot, so again everything's in per square foot of cropland, is given by that profit equation. So it's in profit per square foot he farms. Where x is the amount spent on labor per square foot, y is the amount spent on fertilizer per square foot. All right, the farmer can spend a total of $31.90 per square foot. So that's his budget, right? Every square foot of cropland, he can only spend $31.90. And so that's his constraint. Some of that $31.90 can be spent on labor. Some of it can be spent on fertilizer. When we spend X amount on labor, Y amount on fertilizer, it has to be equal to or less than the $31.90. Now again, we usually set it up as equal to. So in this case, my X plus Y has to be equal to the $31.90. Which again, we set that equal to 0, so X plus Y minus my $31.90 equals 0. That's the constraint equation we need. Alright, so again, applications we typically have to find, but it usually is again a simple linear equation. It involves my X, my Y, and some limit that I'm given. Alright, how many dollars per square foot should be out? So of the $31.90, how much of that should be spent to labor, and how much of that should be spent on fertilizer in order to optimize the profit from each square foot of cropland? Alright, so there's what we want to find, and so now we set it up. So since we got a limitation, we have to set up our Lagrange equation. So again, step 1 is write down my profit. So let me just look over here. So it's negative x squared minus 5y squared plus 10xy plus 4x 2y minus 1100. There's my profit equation. And then it's minus lambda times my constraint equation, which was x plus y minus 3190. Alright, find your first order derivatives and set them equal to 0. Which in this case it is good. Most of our applications will be linear. I will do an example later on that's not linear again, just so you can see another one. Alright, so first derivative with respect. So again, I look at my optimization function, take its derivative with respect to x. So there are 3x terms, so I get negative 2x, zeros away, 10y plus 4, minus lambda times the derivative of the constraint with respect to x. Well, there's only one x value, and so it's lambda times 1, and I go ahead and set it equal to 0 so I don't forget. Alright, now with respect to y, so again I take the profit function with respect to y, so I get a negative 10y plus 10x plus 2, right, there's a 2 here, minus lambda times 1 again, because again there's just the 1y, set equal to 0. And then the constraint equation, or the lambda is always negative 1 times that constraint equation. Right, it is a linear case. There's only x terms, y terms, lambdas, and constants. So just be careful in this case. Alright, I do have constants I have to move over in every term. And so before I go put it in my matrix, I'm going to rewrite it. Right? X term, y term, lambda term equals my constant term. Alright, so in the first equation, it's negative 2x, 10y. I have to move the negative 4 over. Alright, so my negative 4 is moved over, so it's set equal to negative 4, and then I've got lambda times 1, so negative lambda there. Alright, so my first equation. Second equation, again, x first, so it's 10x minus 10y. I've got to move that 2 to the other side, so I get a negative 2, right? Subtract the plus 2, move it to the other side. And that also has a negative lambda. And then the last one's always the constraint equation. I have x plus y equals my 3190. Alright, so there, set it up first. Make sure you do that so that you plug it into the matrix correctly. Remember, it's a 3x4 matrix. Negative 2, 10, negative 1, negative 4 across the top. Positive 10, negative 10, negative 1, negative 2 in the second line. 1, 1, 0, 3, 1.9. Alright, RREF. And it should give you out that nice, neat matrix with your x, y, and lambda, which again, we don't do anything with lambda but find it. And so it's 20, 11.9, and positive 3. Alright, so x is 20, y is 11.9, and again, we did find lambda, we don't really do anything with it. 83, not 38. And so, there's my answer. We spend $20 per square foot on labor, $11.90 per square foot on fertilizer, and it should make sense that those values should be within my limitation, right? I can only spend $31.90. So either the x and y have to come out less than that, or in this case, equal to it. Right? And so it's the equal to case, right? If you take 20 plus 11.90, you get 31.90. Right, then the total profit, well, I've got to plug those numbers into my profit equation to get my profit per square foot. So how much profit did they get per square foot? So again, I have to go back and plug it into the original equation. So again, just make sure you're careful when you plug it in. And so the optimized profit, so every square foot of cropland should yield $275.75 of profit per square foot. Alright, so there's my first example. Alright, we'll stop there. Pick up the next application in the next video.